Hello students, in the last lectures we have studied about electrostatic potential energy, electrostatic potential. In this lecture we are going to find out an expression for electrostatic potential energy of a system of charges. We'll derive a formula using which we can find out the electrostatic potential energy of a system of charge. So let's start it. First we are going to find out the electrostatic potential energy of a system of 2-point charges. It means that we'll consider a system in which there are 2-point charges. As you can clearly see in the diagram, we have taken 2-point charges. First is plus q1 which is at point P, whereas second is plus q2 which is initially at infinity, and we have to bring this charge plus q2 from infinity to a point Q whose position is given by R2 vector. Here the position of plus q1 charge is given by R1 vector, whereas we have to move plus q2 charge from infinity to a point Q whose position vector is given by R2. The distance between P and Q point is given by R12 vector. Now, how to find out the electrostatic potential energy? As we know that potential energy is stored in a body when it is moved from one point to another, or you can say if the body is moved from one point to another against any force. In that case, we'll say that the work done is negative and it is being stored in the body in the form of potential energy. Since here we are talking about the charges, so instead of potential energy we use the term electrostatic potential energy. As you can see in the diagram, q1 plus q1 is at point P whose position vector is given by R1. It means that this charge is brought from any point to this point P. Since this charge q1 was brought from any point in the space to this point, no work was done as there was no other force around it. If we don't consider it, it means this q1 was brought, let's say it is brought from origin. If q1 was brought from origin to this point, no work was done as there were no forces around it. So the work done in moving plus q1 charge from origin to this point can be considered to be as 0. Now what will be the work done in moving plus q charge from infinity to this point? In this case, we have to do work in bringing plus q charge from infinity to this point against the force that is being created by plus q1. So in this case, when plus q2 will be brought from infinity to q, some work will be done against this electrostatic force, and that will be stored in it in the form of electrostatic potential energy. Now let's find out the amount of work done. As you can see, this plus q1 charge is kept at this point, so it will create a potential at point Q. So the electrostatic potential at point Q due to plus q1 charge will be given by q1 upon 4 pi epsilon naught R12, where R12 is the distance between point P and Q. Now the work is done. The work done in moving plus q charge from infinity to point Q, as we have already discussed that plus q charge was initially at infinity and we have to bring it from infinity to point Q. So the work done will be V. W is equal to V potential due to Q1 into Q2. Q2 is the charge which is being transferred. So this, putting these value, will get W is equal to Q1 Q2 upon 4 pi epsilon naught R12. The total work will be actually W net will be equal to W plus W0. W0 here is the work done in moving this plus q1 charge from origin to this point, and as we have already discussed, it will be equal to 0. So the net W will become, or the net work done will become q1 q2 upon 4 pi epsilon naught R12. As this will be the work done against the electrostatic force produced by plus q1, so it will be stored in the form of potential energy. Hence we can say the formula for potential energy is given by q1 q2 upon 4 pi epsilon naught R12. Next we are going to derive an expression for electrostatic potential energy due to a system of n point charges. As you can see in the diagram, plus Q1 is the charge which was brought from origin to point P. So the work done will be 0 as we have already discussed. Next step will be we will be bringing plus Q2 plus Q3 and plus Q4 from infinity to point Q, R and S respectively. The distance as indicated in the diagram between P and Q is R12. The distance between Q and R is R23. Distance between P and R, R13. Distance between Q and S, R24. Distance between PS, R14, and distance between RS, which is not shown in the diagram, it will be R34. So the total work done will be equal to the sum of work done moving from of charge Q2, Q3 and Q4. So first we'll find out work done moving Q2 to point Q. The work done will be potential due to Q1. Here the potential is produced due to charge plus Q1 into the charge which is being transferred, that is Q2. So the work done will be Q1 Q2 upon 4 pi epsilon naught R12, distance R1. Now we will find out work done moving charge Q3 to point R. As you can see, when we move charge plus Q3 to R, it will be against the electrostatic force due to plus Q1 and plus Q2. Initially plus Q2 was at infinity, but now we have moved it to point capital Q. So the work done in moving plus Q3 charge will be against the electrostatic force due to Q1 and Q2. So the work done in moving Q3 to point R, W3 will be equal to potential due to Q1 and Q2 into the charge which is being transferred, that is Q3. Potential due to Q1 will be Q1 upon 4 pi epsilon naught R13, the distance is R13, plus Q2 upon 4 pi epsilon naught R23. R23 is the distance between point capital Q and R into Q3. So we'll get Q1 Q3 upon 4 pi epsilon naught R13 plus Q2 Q3 upon 4 pi epsilon naught R23. Similarly, with the work done in moving Q4 to point S, it will be against the electrostatic force due to plus Q1 plus Q2 and plus Q3. So work done will be potential due to Q1, Q2 and Q3 into the charge which is being transferred, which is Q4. Putting the value, will get this. So finally the total potential energy will be equal to W1 plus W2 plus W3 plus W4, and also the work done in moving plus Q1 charge from infinity, from origin to point P, but as we have already discussed, it will be equal to 0, so we are not taking that into consideration. So finally we'll get the formula for total potential energy, 1 by 4 pi epsilon naught summation of Qi Qz upon Riz, where Iz is equal to 1 up to infinity. So what is the basic way to finding out electrostatic potential energy due to a system of n point charges is just find out the work done in bringing each charge from infinity to a point, then simply add them up. You will get the total potential energy due to a system of n point charges. What if we need to find out potential energy of charges in an external electric field? As we have already discussed, then in case of external electric field, the source charge which is producing the electric field is of no importance. The charge on which the electric field is being applied is of more importance. First, we'll find out potential energy due to a single charge. Let's say there is an electric field as shown in the diagram. As there is electric field, there will be electric potential also. We bring a charge Q from infinity to a point inside the electric field where the electric potential is V. So the net work done will be equal to Q into V. As we know, potential is given by W upon Q. So W will be equal to Q into V. So the potential energy will be Q into V. Since the work done will be against the electrostatic force, so this will be the work done, and it will be stored in the charge in the form of potential energy. Next, we are going to study potential energy of charges in an external field due to multiple charges. As you can see in the diagram, I have taken two charges, Q1 and Q2. This is an electric field which is producing a potential V. First, we will bring the charge Q1 from infinity to a point P in the electric field. Secondly, we will bring the charge Q2 from infinity to a point Q in the electric field, which is at a distance of R12. While bringing the charge Q1 from infinity to point P, the work done will be Q1V, while the work done in bringing charge Q2 from infinity to point Q will be equal to Q2V. But when the charge Q2 is moved from infinity to point Q, it has to do work against the potential due to the electric field and also due to the potential due to charge Q1, which is now inside the electric field. So the work done or potential energy in moving Q2 against Q1 electric field will be W3 Q1 Q2 upon 4 pi epsilon naught R12. This we have discussed earlier. So the total work done will be W1 plus W2 plus W3, where W2 plus W3 is the work done by charge Q2, W2 due to the potential created by electric field, and W3 due to the potential created by the charge Q1, which was now inside the electric field. So total work done or total potential energy will be equal to Q1V plus Q2V plus Q1 Q2 upon 4 pi epsilon naught R12, where R12 is the distance between point Q, P and Q. Next we are going to study potential energy of a dipole due to external electric field. As you can see in this diagram, the red lines are showing an external electric field. A dipole of length 2a is kept such that the center of dipole makes an angle of theta with an external electric field. As we know, if a dipole is aligned at an angle theta with an external electric field, torque will be produced which will try to align this dipole along the electric field. What if we try to rotate this dipole against the torque? In that case, some negative work will be done and that will be stored in the form of potential energy. So let's say the small amount of work done in rotating the dipole through a small angle d theta against the torque is given by dw is equal to tau dot d theta. Tau is the torque and we are doing the work against it. So as we know, torque is given by Pe sin theta. So the equation becomes Pe sin theta dot d theta. Now the total work done in rotating the dipole from theta 1 to theta 2. Let's say the initial angle is theta 1. On rotating the dipole against the torque, it becomes theta 2. So the work done will be integration of d theta dw from theta 1 to theta 2. It will be equal to integration of Pe sin theta dot d theta. Pe is constant and integration of sin theta is minus cos theta. So it will become minus cos theta from theta 1 to theta 2. On putting the limits, we'll get minus Pe cos theta 2 minus cos theta 1. So this is the formula for finding out potential energy of a dipole due to external electric field. What if the dipole was initially at right angle? Let's say this dipole was initially such that it was making an angle of 90 degree with the external electric field. Then theta 1 will be taken as 90 degree. So cos theta 1 will become 0. So we'll finally get work done is equal to minus Pe cos theta. And as we know, A dot B is equal to AB cos theta. So we'll write work done or potential energy is minus dipole moment dot external electric field or the dot product of dipole moment and external electric field.